Okay, so we're moving on to section 7.2 in our chapter 7, random variables. And we're going to be talking about not just what discrete and continuous random variables are, but we want to understand more about them. And to understand more about them means to think about their distribution. And when we think about distributions, going back to chapter 1, well, we want to describe measures of center and measures of spread. So this section is all about the means and variances of random variables. Let's take a look at this example here. It says you play the Tri-State Pick 3. It's a lottery game where you choose a 3-digit number, and the state also chooses a 3-digit number, usually with some kind of popping ball system. And if your numbers match the numbers that pop up, well, you win $500. That'd be a great day. Now, if we call X the amount that your ticket pays you, we could create a probability distribution of this game. Therefore, clearly this is going to be a discrete random variable, because as you see, you either win $0 or you win $500. You can't win any value in between there. Now, if you're choosing a 3-digit number, well, there are 10 digits that the first number could take, 10 digits that the second number can take, 10 that the third can take, telling us that there are 1,000 possible numbers. Well, you didn't really need me to tell you that, because those numbers could be 0, 0, 0, all the way through 999. Now, of those 1,000 numbers, only one of them is going to be accurate. So if you're trying to find the probability of accurately picking the 3-digit number, well, as you see here, 99.9% of the time you're not going to pick the right number, 999 out of 1,000, and only one time out of 1,000 will you actually win this lottery here. But if you win $500. So that's our probability distribution. What we want to do is figure out your average payoff. Now, average, you're starting to think about the mean of what's going on there. Average payoff from many tickets. Well, if you think about that, you're only going to win one time out of 1,000. But when you do win, you're going to win $500 in that round. So you take your $500 that you'd win, multiply it by the probability of winning, and you could also multiply 0, meaning the probability that you don't win, times the probability that you don't win. And you turn it out and you add those two together because they're disjoint events, and you find out that you'll win 50 cents on average for each ticket that you purchase. Now, if you think about that, if it costs $1 to play, well, on each play, on average, how much is the state keeping? Well, if you win on average 50 cents, and you're spending $1, well, that means that the state is going to keep half of your money in the long run. Now, if you put this into the context of, say, a Mega Millions or a Powerball, the state is actually keeping a lot more than half of what you pay. But that's for another time to take a look at. So let's kind of summarize here. We have this mu of x here, and what we're talking about here is that's just the mean of x. It's kind of basic there. It says here some important things. Mu of x does not have to be an actual value of x. Our mean for our Tri-State Lottery was 50 cents. But you can't win 50 cents when you play that game, even though that's the expected amount that you win over the long run. Another way to think of the mean of x, or mu of x, is this idea of expected value, because that's how much you expect to win on each play in the long run. Now again, just like you can't expect the mean to be an actual value, sometimes it will be, most times it won't be. You don't expect that any single value is going to be close to that expected value either. And one more way to think of this expected value, or mean of x, is the weighted average. You've thought about this when you were thinking about GPA or something along those lines. To kind of generalize what's going on, if we have this probability distribution here for this discrete random variable in general terms, and you want the mean of x, well, all you have to do is multiply each possible value by its probability, and then add all the products together. In notation form, we say the mean of x is equal to x1 p1 plus x2 p2 plus ... all the way out to xk pk. Put in more simpler terms, sigma xi times pi. So all this is the sum of all the x's times p's. Now again, this is only true for discrete random variables. If you're trying to find the mean for a continuous random variable, well, if it's a normal distribution, we'll just find the middle. If it's a uniform distribution, find the middle. If it's something that's not normal or uniform, and it's not symmetric either, then you're going to have to choose some other method for figuring that out, and that's something that we'll talk about in a little while. To kind of explore this concept a little bit further, we're going to look at something called Benford's Law. Now, Benford's Law is really more of an economics topic, not a statistics topic, but we're going to use it to kind of explore this idea of expected value. It says if the first digits were truly random, then they would all have the same probability. And what we're talking about here is thinking about if you were to have a business and you would have all of these accounts paid, and all these other accounts that you'd be having values for. And all of those numbers, well, they would have a first digit. Let's say your ledger looked like this, where you had 452, 967, 112. These are all values of money that you brought in. Maybe this was revenue for a particular day. And we would say, okay, just looking at that first digit there, in this small example, we have a 4, a 9, and a 1. If we were to say that these digits were truly random, then we would expect all of them to be equally likely, meaning that we'd have a 1, 1/9 of the time, a 2 as the first digit, 1/9 of the time, etc., all the way up to a 9, 1/9 of the time. Now you might be a little confused, why aren't we thinking about 0? Well, no one writes 0,452, so it's weird to think of having the first digit being a 0. We don't really think that way, so we can just kind of ignore a 0. Now, if we were to find the mean of that distribution, well, that'll just be 1 times 1/9 plus 2 times 2/9 plus all the way up to 9 times 9/9. And you could do that pretty quickly and figure out that the mean is going to be 5. Now, the other way to look at this one is that, well, this is a uniform distribution, so really you're just looking for the middle. The 1 cancels with the 9, 2 with the 8, and keep going until you end up at the middle there. So that works here because it's a uniform distribution. But you could go out and do the probability as we just explained here and find it's 5 as well. Now, if they followed Benford's Law, which Benford's Law is this idea that not all of the first digits are going to be a uniform distribution. In fact, as you see down here, you're going to have a lot more of these first numbers be a 1 or a 2 than you are to have them be an 8 or a 9. Okay? So, in fact, 30.1% of the time will that first number be a 1, 17.6% of the time will they be a 2, and only 4.6% of the time will it be a 9. Now, this might be confusing. Why is this the case? The reason why isn't something that's really too important to us, but basically we're thinking of it as, well, if you're going to have values, generally speaking, they're going to end up in, say, the low thousands or the low hundreds. That's going to happen a lot more than having, say, 9,000 or 900 or 99,000, something along those lines. And that's why the 1 is more likely to occur than the 9. But again, that doesn't really make sense. That's not really the point of what we're trying to get at. It's more of, like I said, an economics topic. Now, if we were to try to find the mean value of V, where we defined V to be this Benford's Law distribution, well, all we would do is take, as we did before, 1 times 0.301, because that is the x value times the probability of x, and that would be for 1, and then add that to the x times the probability of x for 2, and just keep going all the way out. And you might want to take a second to stop the video at this point and actually calculate that there. And when you do find that mean, it turns out to be 3.441. Now, if we think about that, when we had the uniform distribution, the mean was 5, and now here we're saying the mean is 3.441. You might be wondering why that is. Well, if you think about it, it makes sense because there are more values on the lower side, so that's going to pull the mean towards the left. Okay, and then it says the mean of a uniform distribution is at its center. Well, we talked about that. That's finding the mean for the random first digit. For skewed data, as we have here, further calculations are needed. So that's why we found this value in this manner here. All right, and this is kind of just a visual method here of showing what's going on. Here we have if they were all equally likely, so uniform. And here down here we have the distribution for V, where 1 is much more likely than getting a 9. And that's why the means are different. But it takes a little while to get there, but it's not an overly difficult concept there. Now when we talk about the measure of center, that's the mean, but we also want to think about the measure of spread. So we want to think about variance. Okay, now when we say variance, we're talking about sigma squared of x. All right, and just a quick reminder, if you want to get the standard deviation of x, all you have to do is take the variance and square root it. Again, chapter 1 topic really, but I want to make sure we're good on that. It says the variance of a random variable is an average of the squared deviation. Average of the squared deviation. When we say deviation, we're talking about, well, the x value minus the mean. Deviation from its mean. And we want to square that distance, okay, square that deviation, so that's why we square it outside here. And we want to average that. So if we're looking down here, again with our probability distribution, so we're only referring to discrete random variables. If we're looking for the variance, we take, again, variance here, not standard deviation just yet. We take the x1 minus the mean, we square it, and then we multiply it by the probability. And then we take the x for the second value, subtract the mean, square it, multiply it by the probability. And we can write that all the way out, or we could just come in and say that it's the sum of all of the x values minus the mean squared times the probability. And again, this is variance. If we were to try to find the standard deviation, well, we could simply write that out as, say, the standard deviation of x is equal to the square root of the sum of all the x minus the means squared times the probability. All right? So, this will give us the idea of spread. And let's go ahead and take a look at what's going on with this and see how it works. Let's talk about Linda, who sells cars. And it says here we have her probability distribution for how many cars she sells on a given day. And it says here that she sells 0 cars 30% of the time, 1 car 40% of the time, etc. And what do we want to do? We want to find the mean and the variance for this distribution here. All right? So, to find the mean, we recall, we're going to take the sum of all the x's times p's. And to find the variance, we're going to take the x minus the means, square it, and multiply it by the probabilities. Okay? So those are our two formulas, and let's go ahead and take a look at how we do that. For the mean, well, we had 0 cars 30% of the time, 1 car 40% of the time, 2 cars 20% of the time, and 3 cars 10% of the time. So we just multiply the x times the p of x, and then do it again for each of these different x values, and we see that the expected number of cars she's going to sell per day is 1.1. For the variance, we're going to do the same thing for that formula. Again, taking the x value minus the mean squared times the probability for each one. And I would stop it here, try it on your own, and then see if you did it correctly. We see it's x minus that mean that we just found. We square it and multiply it by the probability. And we do that for each of those x values, and we get 0.890. So on average, she's going to sell 1.1 with a variance of 0.89. Now, we want to make sure that we think about how the standard deviation relates to that, because we want to understand the distribution a little bit better. Since variance doesn't have a working definition, we want to usually go back to the standard deviation. And if I take the square root of 0.89, I'm going to get 0.94, oh, that's not 0.9, 9434. So the standard deviation is just a little bit less than 1. Down here are the calculator steps that might help you when you have larger data sets. That might be something you want to take a look at. For now, I'm not going to explore that too much. Let's look at this example here. And again, you just saw me do it. Now would be a great time for you to try it on your own. We're looking at this example called Kids and Toys. It says past experience with many subjects have shown that the probability distribution of the number X toys played with is as follows. And if we look at this, it starts fairly small. Only 3% of kids play with 0 toys. 16% play with 1 toy, and it's going up, peaking at 2 toys, and then it starts to go back down. So clearly it starts low, gets bigger, and goes low again, but we can't say that it is going to be symmetric, so we can't just take that middle value here. Instead, we have to find the mean of there. Now notice here, that's the standard deviation. All right. So stop the video, try these on your own, and then let's see if you get the same values that I get. For the mean, taking all the x times p's plus x times p's, I end up getting an average of 2.68. And a standard deviation, notice I have my big square root, because I'm talking about the standard deviation. All my x times means squared times probabilities, I end up with a standard deviation of 1.31. And again, I'm getting a better idea of this distribution, keeping that word into play there, bringing us back to chapter 1. Make sure that you agree with that. If you don't, check your calculator. It's very easy to miss a decimal or something along those lines in these particular problems. Okay. Now here is what we're going to take a look at in class, these exercises there, and a funny Dilbert cartoon, which you could take a second to read there. I think it's funny because, well, jokes are funny. Now, we also want to take a look at this idea of statistical estimation. When we're looking at these discrete random variables, as we just did, finding the mean and standard deviation isn't so bad. But if we wanted to do the same thing for the continuous random variables, we need to do a little bit more exploration. And really, we're not able at this time for us to find those means and standard deviation. So we'd have to estimate the population mean using some kind of sample. In this case, we're going to take an SRS to obtain the sample mean. And what is it we're actually looking for? Well, we're looking for the height, the mean height, I should say, of all American women aged 18 to 24. Now, if we were to take many samples, well, sure, we would end up getting different means, because if I took a sample of 5, I might get a mean of, say, 63 inches. Somebody else took a sample, they might get a sample mean of 64 inches, and it's going to vary because we have different people in our samples. That makes sense. However, if we were to take all of these samples and put them together, then we would probably get a mean, x bar, that would be somewhere near the true mean, mu. And if we keep taking this sample over and over and over again, or if we keep adding observations, meaning making our sample larger, then we can say that x bar is guaranteed to get as close to mu as we wish, and then stay that close. Meaning, at the beginning, when our sample size is low, we have a greater variability. We have a bigger standard deviation for these different x bars. But as we increase the size of our sample, the x bar is going to get closer and closer to mu, and it's going to stay that close or get even closer. And this is all due to this idea of the law of large numbers. And this is something that casinos rely heavily on to make sure that they make a lot of money. But let's read here for a second. It says, law of large numbers. Draw independent observations at random from any population with finite mean, mu. Decide how accurately you would like to estimate mu, and as the number of observations drawn increases, the mean x bar of the observed value eventually approaches the mean mu of the population as closely as you specified, and then it stays that close. If we look at this here, this is a kind of out of scale, as you can clearly see. We're starting at 1, then we get to 5, and then it's 10, and all of a sudden, boom, it's 50 and 100 and 1,000, etc. Okay? But the point is, as we look at this, when we have a sample of size 1, we're at, I don't know, maybe 64.2, right? With the true mean represented by this dotted line here at 64.5. And as we increase our sample size, when we get it, the sample size to say 5, for this particular sample, the mean is all the way down to 63.5, a full inch below the true mean. And it actually goes below that as we increase the sample size. Again, due to chance variability. But as we keep continuing to increase that sample size, it's going to get closer and closer and closer to that true mean, and it's going to stay there at that point there. All right, and we could explore this a little bit further, and we will with an example in class. But the idea is that as you increase the sample size, x bar gets closer to mu. So let's write that down. Increasing sample size means x bar approaches mu. Well, as we see here, it says the mean mu of a random variable is the average value of the variable in two different senses. It's the average of all the possible values weighted by the probability of occurring. Well, that's just what we were looking at with our examples before. But it's also the long-run average of many independent observations on the variable. So really just two different ways to look at the idea of the mean. Here is when we know all the probability of each individual outcome. Here, well, maybe we don't know it, but we can just observe what's going on by seeing many independent observations. Think playing the casinos. It says the average result of many independent observations are stable and predictable. And that's what casinos know. Casinos know that maybe there's going to be a handful of people that leave each day winning $100,000. But they also know that there are going to be hundreds, if not thousands, of people leaving who lost $100 or $200. And those thousands of people who lost $100 or $200 are going to end up winning the casino more money than those couple of people who won $100,000, because the law of large numbers dictates that that will happen. Now, the problem with that is that some people have this false belief in the law of small numbers. There is no such thing as the law of small numbers. People think that every segment of a random sequence should reflect a true proportion, but that's not necessarily the case. For instance, if you were to flip a coin 4 times in a row and you get a heads, a lot of people who may not be as understanding of number sense might say, well, if there are 4 heads, then the next one should most likely be tails. But we as statisticians know that the probability doesn't change. There's still the same probability, 50% of getting a heads on the next one, and 50% of getting a tails. And we can kind of look at that. It says here, write down a sequence of heads and tails that you think imitates 10 tosses of a balanced coin. Now we could do that. We could look at a heads, and maybe the next one is also a heads, but then there's a tails, maybe another heads and 2 tails, or heads and tails and heads, heads. Did I count 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I did 10. Good job. Okay. Now, if we were to look at this and try to answer this question, how many people included a run of at least 3 heads or 3 tails in a row? Well, I didn't, okay? Just by chance there. I did not have 3 heads or 3 tails in a row. In fact, that probability of occurring is 0.5078, meaning half the time you're going to have a run of 3 heads or 3 tails in a row. But a lot of people who look at casino games or any really situation that is a random variable will think that it's less likely to occur than the 50% of the time. And it says belief in the law of small numbers influences behavior. If you understand how roulette works, okay, you could bet a number in roulette, or you could also just bet a color. Now those colors are red and black. If you're looking at a board and maybe there were 5 consecutive games that produced a red, a lot of people say, black is due, so they're going to bet on the black, and they're going to, well, they might win or they might lose. But whether they win or lose has nothing to do with actual true probability. It's just chance. It's just luck. Okay, they're thinking that it's going to be more likely for the next one to be black, but the law of small numbers is not a true thing. It is not going to necessarily balance out in the short run. In the long run, yeah, sure, there are going to be just as many reds as there are blacks, give or take a couple. But in the short run, that does not necessarily have to be the case. So that begs the question then, how large is large enough? Okay, if you're talking about, well, 20 rolls of the roulette wheel, is that enough? 50 rolls, 100 rolls? Well, it really depends on the variability of the random outcomes there. The more variability, the more trials are needed to ensure that X is close to U. In the roulette wheel example, well, getting a black is just as likely as getting a red. So you don't need as many samples there to get the means close to the true mean mu. But if it's an example more like Benford's law, there's a lot more variability there, so you're going to need to have more samples. All right, and like I said again, casinos understand that. The outcomes of games of chance are variable enough to hold the interest of the gamblers because every once in a while someone's going to win big. All right, but over time, they're going to rely on the law of large numbers, telling you that there's going to be a heck of a lot more people losing money than there are winning money. Okay, and this is the second set of examples that we're going to take a look at for this, and here is another Dilbert cartoon for you to look at there. Okay, so we're halfway through section 7.2. That wraps up this video talking about describing these distributions by finding their mean and their variance, and therefore their standard deviation as well. We'll come back in the next video and take a look at the rules for the means and variances for how we combine these random variables, but that's it for today. And we'll see you in class to talk about these exercises.